inviting me to this beautiful country. I like it a lot. Korea, I've never been here before. Thank you very much. I will give a talk about general relativity, and it's a joint work with Markus Kunze and Gerhard Rhein. And this is actually not yet really finished. I hope we can finish the paper quite soon, but it is about to prove existence of axially symmetric solutions to the Einstein-Vlasov system, which are rotating. So we really would like to have, you think about galaxies, and most galaxies, they think of having some rotation, and that is what we really want to include here. So I should say that from the start, if we go back like 15 years or something, Gerhard Rhein and Alan Rendell, they studied the question about existence of static solutions in the spherical symmetric situation. And by now we know a lot about those solutions. And then it has been, so a few years ago I started together with Gerhard Rhein and Markus Kunze the question to get rid of spherical symmetry. And then we started to investigate axially symmetric solutions. And the first thing we did was to try to obtain solutions which are not spherical symmetric, but axially symmetric, but which do not have any rotation. So that is called a static case. So you can think of a galaxy, which is like American football, something like that, but it's not rotating. Although I should stress that the method we are using is we perturb spherical symmetric solution, so the deviation from spherical symmetry is very small. To go from spherical symmetry to axial symmetry means, for the Einstein equations, big change of the equations. The complexity of the equations get really much worse. I will show you quite some equations here, and some of my slides are more meant just to show you what kind of equations the Einstein equations are, not meant that you should remember them. And as we will see, that we'll also maybe show one situation about the more general situation, how Einstein's equations may look like. Okay, so this is a kinetic meeting, so you know all those things. I just would like to say that in the situation with Einstein equations, the particles we think of in this kinetic description, they are typically stars or galaxies or even clusters of galaxies. And we have the density function on phase space F. And generally, before I go to a particular problem we are studying, how do you formulate the Einstein-Vlasov system? So you take some local coordinates, x and p, in the tangent bundle of the space-time, and you define the mass shell to be those four momenta satisfying this relation. Is there a pointer here?
Yeah, that's button.
Okay. And all the particles in the system, we assume they have the same rest mass. We normalize it to 1. And therefore, we have this relation. And in this model, we are thinking of there are no collisions. So it's a collisionless model. And therefore, the mass shell is invariant on the geodesic flow. So the particles just follow the geodesics of spacetime. And thanks to this relation here, we can express the P0 component in terms of the P1 and P2 and P3 component. So finally you have on the mass shell the coordinates T and 3 spatial coordinates and 3 momenta coordinates. And then you formulate, you write down the Vlasov equation, which is this guy here, and what comes in from the geometry is the Christoffel symbols here. So you have a metric. So maybe I forgot to say that you start with space-time, equipped with the metric G. And the Einstein equations, you can write, they are given like this. This is the Ricci tensor, the scalar curvature, and the metric. And in this talk, I do not have any cosmological constant. I think Alan Rendell will talk later on where he mentioned the cosmological constant. In problems like this, where we study isolated bodies, it has usually not much effect. It's more when you look at cosmological scales and you model the whole universe, where the cosmological constant plays a role. So this left-hand side is a geometry, and you get those quantities out from the metric, whereas this guy is the energy momentum tensor. And depending on which matter model you choose, it has a different form. And the form, when you have Vlasov matter, is given by this guy here, and you raise and lower the indices by the metric. So you have a coupled system consisting of those three equations. And this is the Einstein-Vlasov system. And I should say that in principle it has very nice mathematical properties. The last 2 decades, several global results have been proven for this system. And it was initiated by Alan Rendell and Gerhard Rein, I would say, in the early 90s, the study of the system. Okay, so the particular problem that I'm going to discuss is to construct static or stationary solutions. So when I say static solutions, then we have no rotation. And when I say stationary solutions, we have also total angular momentum. And what I'm talking about today is basically part 2 of something I started together with Kunze and Rein a few years ago. So the first part, when we were able to prove existence of axially symmetric but not spherically symmetric solutions, it's in this paper. And by that time, we could not include rotation. Now we think we can do that. That is for the Vlasov matter. There are some previous results for other matter models. So if you, as I mentioned here, the way you model the energy momentum tensor, it depends on which matter model you choose. So some matter models are better for describing, let's say, galaxies. Some matter models are better for describing as individual stars and so on. And Andreasson, Bike, and Schmidt, they have, first in this paper, they have shown existence of axially symmetric static solutions, so they have no rotation. And then they include the rotation in this paper for elastic matter. That's a different matter model. In both of those models, the Vlasov model and elastic matter, you can have static solutions which are not rotating, but which are not spherically symmetric. In this paper by Heilish, he studies perfect fluid, and if you do not have rotation, then it necessarily is spherically symmetric if it's axially symmetric. So in this case, you cannot have two papers like this. So I should say something about the methods here also. So the engine of all those results, it's implicit function theorem. However, apart from that, the method we use is quite different from the methods in those papers. Of course, we use a very different set of coordinates, and we also work in different function spaces and so on. So the equations look quite different. So we cannot really make any benefit from what have been done here. We use a metric which was first introduced by Bardeen, I think. Maybe not first, but Bardeen is a well-known physicist for when he describes axially symmetric solutions. And since we are aiming for static or stationary solutions, we have no time dependence. So the metric coefficients here, we have in this problem 4 different metric functions. It's the mu, it's the v, it's the mu, and it's the omega. And they depend on the variables rho and set. So it's a standard cylindrical variables here. And the difference between having rotation and not having rotation is this quantity omega. So if we take omega to be 0, we are in the static case. And that we have been able to do. So the new thing is that we have included the omega dependency. They have also kept the speed of light c in the problem because we are going to perturb around the steady state of the Vlasov system. And the Newtonian system we get if c is infinite. So we will use that as a parameter. And the Newtonian potential, so nu here, will sort of play the role of the Newtonian potential as c goes to infinity. Those metric functions, they have to satisfy certain boundary conditions so that you really have something which is asymptotically flat. So far out, away from the body, you want the metric to be flat. And then you should have those conditions. And in addition, on the axis of symmetry, you do not want any conical singularities, so you have to have some regularity condition, and in this case it takes this form. So those are the boundary conditions in the problem. Now we would like to construct static or stationary solutions, and exactly as in Walter's Professor Strauss talk, he mentioned how to construct that for the Vlasov system, and you do the same here. You look for conserved quantities, and in this case you have two killing fields, ddt and dv phi, and then generally if you compute those quantities where g is symmetric, you know that they will be conserved. So the E here is the local particle energy, L is this angular momentum, and then you can, exactly as in the Vlasov system, you can make an ansatz. So if you now say that, okay, let's take any kind of function phi here, which depend on those two quantities E and L, then automatically the Vlasov equation holds. I should say that for the Vlasov system, it is well known that you get all solutions as steady states by doing such an ansatz. For the Einstein-Vlasov system, it is not the case. It was shown by Jack Schaefer that the theorem which goes under the name of Jean's theorem, that you get all steady states by this ansatz, is not true for the Einstein-Vlasov system. But anyhow, you can construct solutions by this ansatz. So if you now have this ansatz, you can plug this form of f into the definition of the energy momentum tensor here, and therefore this T alpha beta would then only depend on the metric functions. So the right-hand side of the Einstein equations will now become a function of the four metric functions. So the f is not in the problem anymore. As I mentioned, we will make use of the implicit function theorem, and therefore we have some parameters, in this case two parameters. One I've already mentioned, that is the speed of light. We call it gamma 1 over c squared. And as I mentioned before, if gamma is 0, you are in the Newtonian case. So when you turn on the gamma, it means that you really turn on general relativity. And then you have second parameter lambda, which turns on the dependence on L. And this L is not invariant under arbitrary rotations. So therefore, if the solution depends on this L, it's not spherically symmetric, but axially symmetric. In order for me to say something about the conditions, which are a little bit important for the ansatz, I have to just say that the ansatz we really take is of this form. So first we do some change of momentum variables here. And then the ansatz we really take is a product. So the first function only depends on the particle energy, and the second function psi depends on the angular momentum. And in the limit as gamma goes to 0, this quantity here will take this form, and if omega is 0, this is exactly what we have in the case of the Newtonian situation, where nu then is the Newtonian potential. So this is the ansatz. So the functions we have to put some conditions on are the phi here and the psi. And the conditions we put will not say so much about the first. This is a sort of a standard cutoff assumption. And of course, you should also say that if the phi you take should be such that you really have compactly supported steady state of the Vlasov-Poisson system. That is the state we would like to perturb around. The most important condition is phi 3 here. It says that we require this to hold, where this n stands always for the Newtonian situation. But this an is this integral where you take the derivative of phi and you evaluate this integral, and then this should hold. So this is very essential, and one central part of the proof is to show that there really are steady states to the Vlasov-Poisson situation satisfying this relation. And for the psi, we just say that it should be compactly supported, and if lambda is equal to 0, it should be 1. So before I discuss the strategy and the difficulties, just let me say then the result that we have. So we are now able to construct solutions, two-parameter family of solutions, mu b, mu, and omega. Those are the metric coefficients. And if the parameters are 0, we obtain the Newtonian steady state. And if they are non-zero, you get a solution of the Einstein-Vlasov system, which is not spherically symmetric. And if you take some careful choice of psi, the total angular momentum is non-zero. And the matter distribution is compactly supported both in phase space and in space. You really get some galaxy. That part is important because if the solution extends all over the space, you cannot really call it a galaxy. So I should make some remarks here about this theorem. So first of all, the smallness restriction here on lambda means that the states that the solutions we construct, they are close to being spherically symmetric. This parameter is also in some way undesired, because you really would like to get in a situation where gamma is equal to a definite number, because c is really the speed of light. In this case, since we apply the implicit function theorem, gamma can be very, very small. However, if you have a solution to the Einstein-Vlasov system, then there is a rescaling of the following type. This means that having such a solution, you can actually obtain a solution with c to be being a definite number. If you have normalized things, it should be 1. So you really get a solution of your real problem, so to speak. Okay, so the strategy that we have tried to apply and which is sort of the following. First of all, you have to find the Einstein-Vlasov system. And working on the Einstein equations is a little bit different from studying, for instance, the Schrödinger equation or the Boltzmann equation. Those equations, they look the same when you come to your office every morning. The Einstein-Vlasov system do not, because the explicit form of the equations vary a lot depending on the symmetry assumptions, on the gauge conditions, and so on. So the first thing you should do here is to really find the equations. And it turns out that the Einstein equations is an overdetermined system, so you should find a reduced system to which you want to apply the implicit function theorem. And it's sort of not clear how you choose this reduced system. And then you do analysis and try to show existence of solutions to the reduced system. And then at the end of the day, you go back and try to show that actually you have now constructed a solution which solves the full system, not only the reduced system. And so I should say, I don't know what time here is. Have one. So, yeah, I'm just planning it. So I just want to maybe show you one thing which I find a little bit interesting concerning how you find the Einstein-Vlasov system. So, if you have a lot of symmetry in then the Einstein equations become very simple. You can write it down in 2 lines. For instance, in cosmology, people look at homogeneous solutions which are isotropic, and then there is only one metric function and only one variable, time, and then it's very easy. But, and then you can look at spherical symmetry, then it becomes a little bit more difficult, but not that much. And then the step, as we will see soon, to axial symmetry is quite dramatic. But one should be aware that the Einstein equations, they can really look horrible, in the sense if you really write them out. And nowadays you have softwares you can make use of to derive them. And I gave a talk, for example. So typically when you start a new project in Einstein-Vlasov for the Einstein equations, you use Maple, and Maple is very efficient. You really take your metric, and in this case I have I made up an example to show how horrible they can look like. So generally you have 10, you could have had 10 metric coefficients. In this case I have chosen 5, A, B, C, D, and E. And generally they could depend on 4 variables. Here I have only let them to depend on 3. Then you plug this metric into Maple, and you ask Maple to produce the left-hand side of the Einstein equations. And then what you get is this stuff.
That's the notation of the graph, so that's the equation
So this I find a little bit interesting, because normally when you see things about Einstein equations on television, they only write in a very simple form, as I showed you before. But of course, you can work on those equations even if they look horrible. You don't have to write them out. Right? You can work on large matrices, but you don't have to write out every component. But sometimes, if you can write out the equations explicitly, I think so far, the deeper results have been obtained, I think, in these cases where you really can have an explicit understanding of the equations. Okay, so what are the difficulties in this project? So we have been doing this project for quite a while, and we have encountered many difficulties, I would say. So, and it's really, those points are really connected. So we have had problems to satisfy all the boundary conditions. We have had problems to identify appropriate function spaces and solution formulas. We will see the equations soon, and it's not always clear which way you should solve them. We have to be able to show that the conditions for the implicit function theorem holds. That is, we should see that the map that we set up is well defined, and actually, in this case with rotation, this turns out to be the main new difficulty. We should see that it's continuously Fréchet differentiable. You don't expect any problems here. However, as Alan Randall, maybe also some other person in the audience is aware of, in the static situation, we had almost a finished result where we had identified not the correct reduced system, and it turned out that this part was not, couldn't carry this through. So it was surprising that this was a really problem, that it can be. Here you expect the problems to be, to show that the linear map is 1-to-1 and onto. And here is exactly where this special condition, what I call phi 3, on the ansatz function is central. And to show in the end that all equations hold, there are some general principles that you make this very plausible, but when you really should do the details, you can enter into problems, particularly some regularity problems. Okay, so now I just want to say what you get when you put in the metric I have chosen into Maple to see what kind of equations you get. And you have 4 metric coefficients, and first you get those 2 equations, that is for mu, and this is for b. I should say that those equations are not the components of the Einstein equation. So the Einstein equations we usually call, so it's not that this equation is, for instance, G00. It's a combination, because you see that different parts of the n-dimensional tensor show up here. And this is the equation for B. And then there is an equation for omega. And then there is an equation for mu. And then if you take psi to be a linear combination of mu and mu, you also get those 2 equations for psi. So this is what you get from Maple. This is what you have to handle. And the matter terms, what do they look like? We have this ansatz with this product in phi and psi, and you plug it into the n-dimensional tensor, and you get those expressions. And you note that the metric coefficients appear many places, in particular in the integration boundaries here. So m depends on the metric coefficients. So this is what you're sort of, what's facing you, right? And now you should identify, since you only have 4 metric coefficients, you would like to extract 4 equations out from those 6 equations. So this is what I say here. So the Einstein equations are overdetermined, and we should identify a subset of these. And one has to be careful here. We have made, beginning of this project, we made sort of not good choices here. I think we have made a good choice by now. So what we do is first we, before we do the reduction, we just introduce a new function h, which is related to this metric function b in the following way. That is, the equation for b sort of takes this quite simple form. The reduction we do is then that we combine the two equations for this psi, and we drop the mu equation. So the four equations we then get are those. So this is what we call the nu equation. This is the h equation. This is the omega equation. This was not present in the static case when we did not have rotation. And this is the equation for psi. And the matter terms, as you saw before, in this case I have called the matter terms not t anymore, because they are multiplied with some factors, but basically they are the same as you saw before, expressions of this type. Okay, and then I will just say very quickly the function spaces that we are work on are roughly this. So we have chosen to work in Hölder spaces, and the situation for the omega is a bit different than from the others. I should also say that you see that some of the function spaces, they are in R3 and some are in R2. So depending on which equation we consider, we prefer to look at it. For instance, the equation for nu, we like to look at as an equation in R3. However, you see here it's natural to look at it as an equation in R2 because it's just a two-dimensional Laplacian here. Of course, when we are having the regularities in R3 and R2, when you should go between these situations, you have to be careful. But there are of course lemmas that you can apply. And the norms are of course basically the standard Hölder norms here, but we also add some decay conditions on the functions here. And then we construct the full function space by this, and here you see the Hölder norm is this guy here, right? And I just say very quickly also that in the proof it's important to know that you can stay close to the solution that you linearize around. And I mean, and therefore, and there are some results that you can rely on to say that if you look at this set, where those quantities now are close to the Newtonian steady state, then you know that the matter terms which appear, they are compactly supported in a ball radius r, where r is a certain fixed number. So therefore now we can construct a map from this set, the neighborhood of the steady state, so to speak, to this function space x. And in order to do that, we would like to write down solution formulas for the four equations. Remember, we have four equations. This was the new equation. M1, I will show you in a moment, is a matter expression. And here we have used the standard inversion of the three-dimensional Laplacian. See the kernel here. Here, the equation for h was a two-dimensional Laplacian, and therefore we have the log term here. The equation for psi was of a different nature, and it's this form, where g is a quite long expression. And the new thing with the rotation is this omega equation. And the k here is something which is called, takes this form, where q1/2 is the half integer Legendre function of the second kind. And this we have no, we didn't know at all what to expect when we looked at this equation originally. And I should say that it was, I found it a little bit funny when we did this originally. So we had, if you go back to the omega equation, as this form. So basically, you have a right hand side. You don't know if you should sort of put this on the right hand side or and so on. But what we did was we sort of took an arbitrary right hand side, or basically 0 here, and then we took the Laplace transform so that we got an ODE, and then we were thinking, okay, what do the solutions of this ODE look like? Because we were interested in some properties. And therefore, we put it into the maple, and we wanted to solve it numerically, not analytically. But then we pressed the solution button, and then maple asked us, do you want to solve it analytically or numerically? There were two choices. And we couldn't resist not to press the analytic button. And then it suggested that the solutions was a combination of Bessel functions. And then we could say that after transformation it was really Bessel's equation. And then when we sort of got back to the two-dimensional situation by redoing the Laplace transform and so on, and using some relations for special functions, it turned out that you end up with this guy, which is called the half-integral Legendre function of the second kind. And I should say that you necessarily have to do a lot of estimates of this guy. I hope I will show you something of this at the end. And all the time when we have done those estimates, we have worried that maybe this is not correct, because we sort of found this solution formula by ourselves, and it was quite some computations behind it. So we worry that all the estimates we're doing, maybe they are useless. But I should say that quite recently I met, Gerard and I met in order to complete this paper, and then we also really tried to show that the solution formula is correct, and it is. So I have no doubts that this is right. And you see also here that you have generally the bad thing in this problem is what happens at the axis. So you see that you have 1 over rho to the power of 3/2 in this kernel here. Okay, so also in those expressions there were some matter terms, M1, M2, and M3, and there was this G function, and they are then those huge expressions that we had before, and the G is just some kind of big expression in metric coefficients. So now we finally have this map that we have been looking for, that we will apply the implicit function theory. So those were the solution formulas, and you want the map to be such that it should be 0 at the solutions, therefore you simply subtract the G's from the given ones, right? So and now the proof, when you have made this definition of f, the first thing is you have to check that this f is well defined. That is, if you now put in functions from this neighborhood U, will you end up in the space X? And the main new difficulty when we have included the omega is really this point here. Because if you remember the space X, it contained many regularity assumptions, and it contained decay assumptions. And therefore we really have to be able to do those estimates involving this half-integer Legendre function of second kind. So that has been the main new difficulty. And next step, you want to see that the steady state that you perturb around is really a solution of this map, and this is easy. It follows from the setup, basically. And then you should see that this map is continuous and continuously Frichet differentiable. And as I mentioned before, you don't expect it to be problems here, but it could be if you have done a bad choice of your reduced system. Step 4 you expect to be problematic. Here is when you want to show that this derivative of f is 1 to 1 onto, and this linear map takes this form. I have only here written out what L1 looks like. It's the most essential part, and here is exactly where this AN comes in, which was part of this condition 5.3 with the ansatz function phi here. And it turns out then that if under this condition 5.3, if this holds, then we can show that the map is 1-to-1. The full map, actually, not the L1, but full map L. And in order to see that there are such steady states satisfying this relation, we have to do an analysis of the so-called Emden-Fowler equation. Maybe I have time in the end to say something about that. And the onto part essentially follows from the fact that map L1 is compact. And of course, this is something we had in mind all the time when we put up the function spaces and the solution formulas. We really know that at some point we need to do the onto part, and therefore, in order to do that, it's of course extremely helpful if we have compactness. So that is sort of, it's always some kind of balance in what you should put into the function spaces and what you get out. And okay, so we now can apply this implicit function theorem, and we get a solution to this reduced system. And as I mentioned before, now we need to show that the solution to the reduced system is actually a solution to all the Einstein equations. And this part, I think I maybe skipped this part, but basically it has to do with what you define this guy here, G alpha beta minus this, so you see that when this is 0, this is the Einstein equations. What we have solved, the system we have solved now, the reduced system, expressed in those E alpha beta is really this one. And then, together with the Bianchi identity, we know generally that this holds. One can finally obtain a linear PD for, let's say, one of the components. In this case, we have chosen E12. And using the boundary condition at the axis, it follows that this is actually 0. And therefore, then we can go back and see that each component actually vanishes. So originally, we only knew that we had this, but we want to say that E00 is 0, E11 is 0, E22 is 0, and so on, in order to say that all equations hold. Okay, now I am in the stage where I would like to say something of the analysis behind those things. And so now, as I mentioned before, a new thing in this, when we have rotation, is this omega equation. And as I mentioned before, it took this form where k was this thing with the Legendre function. And I have now abbreviated this guy here by q. So this is something which is basically given. I would say that this M3 is not completely obvious what regularity it has. It's a matter term, but it has a bad factor, 1 over rho in front of it. But it's possible to obtain sufficient regularity on M3. And we want to show now that this map is in this space X4. So, and here we have some regularity conditions and decay conditions. And as an example, which is quite typical, I have chosen to do this. Take one derivative of rho with respect to G4 and try to show that it is bounded. Because I would like to see what the main point here is. So we need some information about what does this half-integral Legendre function look like. And it has a singularity. when the argument is 1, and it's also, we need to know how it decays. And if you look it up in the standard table, special functions, you only get a series representation in what's called hypergeometric Gauss functions, Gauss hypergeometric functions. So it's very confusing. However, in the end we have found some integral representations, and what we have been using is this one. And there are relations, since we also need to take derivatives on this, those derivatives can be expressed in terms of those through this formula. And then we can obtain some asymptotic information. So basically, the behavior is like this. But what's interesting here is the following, because what is really essential here is some cancellation. And so if you go to a special function book, you will maybe get those kind of asymptotic behavior given like this, for instance. So this is for when the argument is large, basically, and this is at the singularity. But as you see, this is not sufficient. It will become clear when you do the estimates that this decay is not sufficient. Must be some better thing. And what happens is that there is actually a cancellation. So you really have to use this integral representation formula to derive by yourself the real asymptotics. Because if you combine this, it's not 1 over chi to the 3 over half anymore, 3 over 2 anymore. It's much, much better. So this is very essential. And when you take the second order derivative, this combination shows up. And again, you get cancellation here. So if I do what happens here is really this: we will fix rho z, and we will take a small rho, because that is the difficult case. And for some technical reasons, we choose it small. And you may perform a derivative, and what comes out is this guy, where psi sits here as this form. You can compute to see what it is, and it takes this form where this A is this guy. And therefore you see that you have A is minus 1 plus something which is a rest term. And you see the rest term here, I said that small rho is the bad guy. But here is, you have some powers of rho, so this is basically the good guy, although it is singular, because this can become 0. Some part of the integration domain. But if you look at the first dominating part here, which is minus 1, and you plug it in here, then you exactly get this had this cancellation property of the Legendre function. So so you get down here this guy, and this is the nice thing which decays like 1 over chi to the 7/2. Plus this rest term. And the rest term would have been good if it was not for that it could still be singular. And then we make a certain split of the integration domain. And in the end, we are able to find a bound here of this type, which is sufficient. And yeah. So should I can, one more minute? Okay. So the last minute I would say something about this condition 5.3, that there are steady states satisfying this condition 5.3. And what we do is to construct polytropes of this type. And it turns out that if we study such polytropes, it should satisfy, the Poisson equation takes this form. And the n, so the k here was allowed to be in this regime. And if we now introduce n, it's allowed to be here in this regime. And this guy set then implies that this should satisfy this equation, which is basically the Emner-Fowler equation. And our condition now on this an becomes this guy here. So set satisfies this equation, and we have to know that this holds. where n is not allowed to be more than 5. And what we do here is, in the analysis, we introduce a quantity w, and our condition is equivalent to say that the maximum of this w should be less than 6 over m. And then the analysis of this Emden-Fowler equation leads to the following inequality, and I found it interesting because when we did this the first time, we had no idea if we were close to this or not. It could be whatever. And it happened that we obtained this formula, and we put in n to be 5, and this means that max w is this guy, and then you looked at this expression the first time, and you were not sure is it less than 6 over 5 or not, and it turns out it's just barely smaller than 6 over 5. So therefore we were able to find that there are such steady states. So that was a happy ending. So I thank you for the attention.
So is there any question?